Hello everyone. This tutorial is going to be about gradient descent in PyTorch for people who want to use this incredibly powerful software that's been developed for neural nets, but who don't actually care about the neural nets. So Torch has a very good implementation of gradient descent, and you don't need a neural network to use it. So I'm going to show a few simple examples of how to do gradient descent using Torch tensors. And this is geared towards people who, are familiar with Python, maybe have done a little bit of NumPy, who know what the gradient descent algorithm is, but who don't need the complexity of neural networks. They just need a simple first-order optimization technique to minimize some objective function, right? Okay, so as an example, I'm going to do something a little bit strange. I'm going to compute the median of a set of numbers in kind of roundabout way. Now, the general definition of a median, you could sort if you had a finite set of numbers and pick the one in the middle, or the two in the middle. But the general definition is actually a median, M, of a set X is the number that minimizes the sum of absolute differences to M, or between M and all elements in the set. So what I'll do here is I'll start right away in Torch. I'll make a set of numbers. Actually, I'll make it a little bit more systematic. So what I'll do is I'll say t is equal to torch.linspace. So I'll make a little smiley up parabola. Say maybe just 1,000 samples of it. So I'll say here my x is equal to, I'll just say t squared. Okay, so let's just look at it real quick. So there's my samples. And actually, just to highlight the fact that they're actual samples, I'll plot a stem plot. There's a bunch of samples. Okay. And I would like to know the median of this. Well, of course, there is a built-in function in Torch that I could use. And I could just call it, and it tells me the median's should be about 1. If I look at this, I can see that half of the values are above 1 and half the values are below 1. But I can also use this definition, and so I can try, let's say I was going to kind of guess and check. I could say, all right, well, what if the median were 0? Let's see, what are the sum of absolute differences to 0? So let's make m 0. I could say, okay, print torch.sum, torch.abs, x minus m. So what this is going to do is it's going to element-wise subtract the median from every element in x, take the absolute value of all those, and then sum them all up. So if m is 0, we get this, about 1336. If I put the m at 1, I see I get a smaller value. If I go up a little bit, I start to get a larger value. So it seems like the minimum is occurring around 1. Now, gradient descent will be able to find that automatically starting from some initial guess. And actually, what's really cool about AutoGrad is so AutoGrad, the system for doing gradient descent for composition of functions in Torch, it can handle things that are not differentiable, like at certain points, like absolute value. It kind of just shoots right past the point of non-differentiability, and so you don't even have to worry about some of those details. It's very cool. So let me show you how to set up an optimization that would automatically find our magic answer of 1 here. So what I'm actually going to do is make my m be a Torch tensor of a single element. All right. So before so this is actually a Torch tensor, then an element y squared. So if I look and actually print x, I'll see that that's a Torch tensor, a one-dimensional Torch tensor. If I were to print the shape, it would show me that there's only one dimension being used. I'm going to create a one-dimensional tensor of a single element, so it's really almost like a zero-dimensional tensor. So I'll just say m is equal to torch.tensor, and whatever I want my initial guess to be, right? And this tends to be pretty important, what you start your initial guess to be. Now this is a pretty simple problem. This median minimization problem, this turns out to be a convex function. So there's actually going to be a global minimum that is the only minimum that's there. But in general, you'll have more complicated functions that, there'll be a lot of local mins, and the gradient descent will settle into one of those, and so it's important that you start by near a good local min. Okay, so just to tell you, it's kind of important where you pick to start. But here, it doesn't really matter so much in this particular problem. I'm going to start at 0, guessing that 0 is the median. It's definitely not, right? We know it's 1, but I'll start there and see what this does. Now, one thing I need to do is I need to make this variable be differentiable. Okay, so I need to let Torch know that it's able to take derivatives of this variable. And so I'm going to say dot, okay, so first I'll make it, and then I'm going to say m dot requires grad underscore. So I'm going to call this little method here and say that this requires grad. Okay, so I need to be able to take the gradient of it. Now when I print it out, oh, it says, okay, only tensors of floating point types, so I guess I have to make this 0.0. Okay, so now I see this extra little flag here that it requires the gradient. Okay, so Torch needs to know about that. Okay, so the next thing I need to do is set up an optimizer object in Torch. And so what I'm going to do is say optimizer equals torch dot optim. Yeah, dot. Okay, so now I've got a few choices of types of descents that I can do. I'm just going to use a really popular one for now called atom, which is a little bit better than just straight gradient descent because it kind of keeps track of where it's going. And this has what's called a learning rate. So it's like the step size. How big of a step am I going to take against the gradient, right? So the gradient's going to point in the direction of steepest ascent of my objective function. And so I want to actually, if I want to minimize it, I need to go against that. So the learning rate tells me, okay, by what factor of the gradient are you going to step against it when trying to optimize this? So I'll start with, 0.001 here. And then the other thing I need to do is I need to say the first parameter to this optimizer should actually be a list of all the things that I want the optimizer to be able to differentiate. So in this case, I'll put m in there. I could have other variables too. Usually people put neural networks in here. So all the, these neural networks with a whole bunch of parameters they'll put in there. But here I just actually have a very simple, just a single parameter. Okay, so that sets up my optimizer. And now what I need to do is make a loop that continues to do little steps of gradient descent over and over again. So let's say I wanted to do some number of iterations. Let's say 1,000. So let's say for, I in range number of iterations. Okay, so the first thing I need to do is I need to zero out any gradients from previous steps. So this is important. What happens is AutoGrad and Torch actually accumulates gradients over a whole bunch of different functions. And you need to tell it when to clear that information. So it's going to reset the gradients of all the variables that it knows about at the beginning of each loop. Because now we're starting over and we want to compute the gradient. We might have changed m and we need to recompute the gradient. So that's the first thing you always do. So clear accumulation of gradients from previous steps. All right. Now what I need to do is devise my loss function. So maybe I'll say step 1 here is clear the gradients. Step 2 is compute the loss function. This can be whatever you want. I told you here what it is it's I'm trying to minimize the sum of the absolute differences between all my elements in X and my M here. So I'm just going to say that my loss is equal to this. And now what I can do is I can actually say, well, first of all, okay, if I were to do that, yeah, let me actually keep track of the losses as I go through, because I want to plot some function that shows me what happens. Hopefully this loss is actually decreasing as the optimization goes forward. So I'll say, okay, every time I do this, I'll say losses.append loss.item. And actually the .item is because this is like a differentiable thing. I want to just take out basically the floating point value associated to it. Okay, so I'm going to do that. But now what I'm going to do is say loss.backward. And here's the really magical step. So this does gradient, this does backpropagation, or in other words, just the chain rule. From whatever this loss function was, it'll follow the chain rule all the way back through all the differentiable parameters, and it'll say, yeah, this is what the step that computes the gradient, right? So yeah, step 1 was clear the gradient. Step 2 was compute loss function. Step 3 was actually compute gradient of loss function with respect to all parameters in the optimizer. All right, so in this case, again, we only have one, but you can have lots of parameters here. Okay. And finally, you need to actually do the thing I mentioned a second ago, which is take a step of the optimizer against the gradient to minimize. the loss function. So again, this is just a magical single line of code, which would be optimizer.step. All right. So hopefully I got this right. Let's see what happens when I run this. Okay, it was pretty fast. Let's actually see what answer we got. So what I can do is I can print out m, and then I will plot the loss curve over time. Okay, so actually it's not letting me plot, oh, it's interesting, it's not letting me plot the loss, because I said loss.item, but I think I need to say loss.detach.item. So it turns out things that are differentiable, or part of differentiable functions in Torch, you have to take them out of differentiable mode in order to be able to do other things with them, like plot them. Okay. Did that still not do it? It says, okay, so maybe this whole thing. Oh, no. This was okay. I meant to plot losses. Okay. But anyway, that was important. If I wanted to just like plot this one thing, I would have to say detach. And I would have to spell it properly, of course. But I don't just want to plot the whole thing. I want to plot losses. Okay, this array. All right, so this is cool. So the loss started off, we saw it was about 1350 when I started off at 0. And I can see this is doing better and better and better. But actually it hasn't quite gotten there, right? I can see the loss probably could still go down a little more. And I know what the answer is supposed to be. It's supposed to be 1, and I see this didn't quite get there. So there's a couple things I can do. I can increase the number of iterations. It'll take longer, right? But eventually it'll settle down. Another thing you can do is actually, try to use the same number of iterations, but increase the learning rate. So take bigger steps each time. And so this actually seemed to work pretty well. Problem is, if you make the learning rate too big, then you'll start to get some oscillations. So you see, I made the learning rate kind of huge here, and yeah, some weird stuff can happen because what will happen is you'll be jumping back and forth. You'll be taking steps that are so big that you're going to go back and forth on either side of the minimum. So there's kind of a sweet spot that you'll end up finding for these kind of gradient descent problems. Actually, here it seemed about probably that a fairly large. This is actually, yeah, 0.1 is too big. Maybe 0.01 seemed to be a pretty good one, and I was able to converge. It looks like probably in only about 250 iterations I got there. Maybe need to go a little bit more than that. Alright, so there's just one more thing I want to tell you about that's kind of important. So let's say I did like an obscene overkill number of iterations here. I can go to a smaller learning rate because I'll probably get there. Okay, so this is taking a long time. I can time how long it takes. Let me actually, yeah, so I like to, this is the kind of the way MATLAB used to do it. They would say tick and then tock. And so, did pretty well. I think 0.998. Let me see. If I did torch.median x, yes, okay, that's pretty much spot on. At least the first 3 significant digit. So that worked really well. But, that's a lot of iterations, and to compute a median, that's grossly inefficient. I mean, this is not the way you want to do the median anyway. But, oops, let me import time here. Yeah, okay, so I'll do that again. I'll record what the time is. But so, what I want to say is, this is doing everything on the CPU by default. And if we have Torch configured to use our GPU, it can work a lot better. So let's see. So this took 10 seconds. I'll take note of that. So 10 seconds, or maybe about 11 seconds for the CPU. But it's possible to copy all the tensors over to the GPU if you have access to it. So to show you, you got to check this first. You have to say torch.cuda.is available. For CUDA, for example, that's what I have. So I have it, so that means that what I can do is say, yeah, let me get rid of that. I'll put the import time up here. And what I can do is say, after I make x, I'll say, now let me show you actually a couple things I could try. So I could say x is equal to x.to CUDA. That'll move it over to CUDA. So let's clear this all up and start over here. So first I'm going to make it on the CPU, but I'm going to move it over to the GPU. And now, actually, it's not going to let me plot it. It's going to complain. It says, can't convert computed to NumPy. So it turns out, okay, once you put things into the GPU mode, you actually have to put them back into CPU mode before you go to plot them or do other things, maybe using NumPy. So that's one thing that's a bit annoying. The other thing is you got to make sure that you know, everything that you deal with. So if I were to try to do this now, it's going to complain because it says expected all tensors to be on the same device, but found at least 2 devices. And so, you know, in this case, the x, kind of the constants that I'm checking to compute the median, that's on the GPU, but m is on the CPU. And so a way to do this that's kind of portable is to actually just say m is equal to m dot 2x. This will put my differentiable parameters onto the same device as x. So if they're both already on the same device, this will do nothing, but if they're on different devices, it will actually take care of that. Oh, but now it says, okay, can't optimize, actually, okay. I don't want to get into this right now, but you actually have to, I'm going to have to put this on the device first. Okay, before I say that it's required grad. So let me just, I'll write it like this. All right. So, yeah, so this is putting on the same device, and this is making it differentiable. Okay, so let's check. That should be okay now. Yeah, all right, so anyway, now it's going to do this optimization. I don't actually know if it's going to be that much faster in this example, but, I mean, technically this operation can be parallelized. So, well also, okay, to be honest, I'm using my GPU right now to record this video, so that might be screwing things up too. Okay, so amazingly, this is going even slower, but, all right, but you would really know that, you would notice the difference if you had huge tensors that could be parallelized. So it's just an important thing to know about how to put this on your GPU. Okay, but that's all I got for now. Maybe I'll just put it back on the CPU. I'll make the device be a variable. And I will, you know, put this code in a state where it's actually choosing reasonable parameters. So 1,000 iterations learning rate, 0.01. Okay, so that's, I'm going to link to a gist with that code. So hopefully this helps people. And yeah. If I have a chance, I'll try to follow up with another video. All right, cheers, everybody.